Academy. So myself Khadar Basha here, and today we are going to see an important topic of synchronous machines, which is armature reaction. To understand many topics in synchronous machine, the most important topic is armature reaction. Particularly, if you want to understand very well the parallel operation of alternator topics, you should have a good knowledge or good information from armature reaction first. So many times in previous JE examinations we have most of the times questions related to armature reaction, and whatever further the characteristics or voltage regulation topic or parallel operation, anything, mostly it depends on the armature reaction topic only. So that's why I want to give now some information regarding the armature reaction in detail. Let's see it is, and this armature reaction will be there in synchronous as well as in DC machine. In both, conceptually it is same, no change, no difference, but one important difference between these two DC and synchronous is, in DC machines this armature reaction does not depends on the loads, because what are the loads we are connecting to DC machines or DC generators? Particularly resistive loads. Loads are resistive in nature. But in case of synchronous machine, we have different types of loads. We can connect in synchronous generator a lagging load or leading load or UPF load or purely inductive load or purely capacitive load. Any type of load we can connect for synchronous. So let's see first what is definition of armature reaction. So this is the armature reaction is nothing but it is reaction between two fields. In every machine we have two fields. Let us take DC and synchronous. We have two fields here. One is armature flux and main flux. Armature flux and main flux. The effect of armature flux on main flux is called armature reaction. The effect of armature flux on main flux is called armature reaction. So the effect of armature flux on main flux at a specific power factor of load. Particularly for synchronous generators, we have to define at a specific power factor of load. But for DC machine, same statement, directly we call the effect of armature flux on main flux, that's it. And there we don't consider any power factor variation, okay, in DC machines. But only in synchronous, we have to consider at a specific power factor of load, because how many types of loads we can connect to the alternator? Any load we can connect, as the rating is given in volt ampere. Any type of load you can connect, like UPF load you can connect, or ZPF lagging load you can connect. What is ZPF lagging? UPF means resistive load, purely resistive load. ZPF lag means purely inductive load, 0 power factor, 90 degrees we get, cos 90. And 0 power factor leading, nothing but purely capacitive load it is. Purely capacitive load, and like that we can connect a lagging power factor load and we can connect a leading power factor load. Lagging power factor means RL load it is, and leading power factor means RC load, combination of resistor and capacitor. Leading power factor load it is, okay. So like that, whenever the loads we are changing, the reaction will change. But in DC machine, it is not depends on power factor first, only resistive load we connect. So there we have the fixed reaction in DC. What are that? Two effects of reaction are demagnetizing and cross magnetizing. But in synchronous machines, additionally we get one more effect, that is magnetizing effect. That effect will come into picture here due to that capacitive loads in case of synchronous generator, okay. So we have to consider this power factor variation. Based on different loads, reaction also will change. Now we will observe each case here. With UPF load, what type of reaction? With the inductive load, what type of reaction? So with that type of load, reactions will change. So how it is changing, now we will observe it, okay. And here one important question I want to say is, in DC machine, armature flux located in rotor. Armature flux will be in rotor, main flux will be in stator. But in synchronous machine, main flux will be in rotor, armature flux will be in stator. Generally we prefer that one in case of synchronous, okay. main flux will be in rotor, armature flux will be in stator for synchronous machines. Okay. Now, here one important question is, what is the speed of this armature MMF or armature flux with respect to stator or with respect to main flux? What is the speed of armature flux with respect to main flux in both DC machine and synchronous machine? The answer is 0. The speed of armature flux with respect to main flux is always 0 in both DC and synchronous. So in case of DC, you take armature flux will be on rotor, main flux will be on stator poles. The speed of this armature flux with respect to main flux is 0. So they look stationary each other. Always in any machine, the two fields rotating, the two fields with respect to each other looks stationary. Because you take example synchronous machine. In synchronous machine, the stator RMF, nothing but armature flux it is, 3-phase. So whenever 3-phase load is there, a 3-phase currents will flow in the winding, RMF will develop, and that RMF nothing but armature flux only. This armature flux is rotating at synchronous speed. Armature flux rotating at synchronous speed. And what is the rotor speed or main flux? Main flux is in rotor. That rotor we are rotating with mechanical input, turbines. At what speed we rotate? Synchronous speed. Now what is the speed of both? Same, in same direction. What is relative speed? 0. The two fields looks each other stationary each other. The two fields look stationary each other because both are rotating in same direction at same speed. Same with respect to DC machine also, but in DC machine main flux will not rotate, that is in stator. Armature flux, armature is rotating clockwise, but armature flux rotates in anti-clockwise there. That's why that armature poles look stationary with respect to this stator or main flux. So simply remember, the speed of armature flux with respect to main flux is 0 in both synchronous and DC machines. Okay. Now let's see one by one. First, case 1, if load is resistive load, what is the type of reaction takes place? So for synchronous, advantage is we can draw the phasor diagram for each case, and directly we can observe from phasors how the effect of armature flux on main flux. Directly we get. But in DC machine it is not possible. So we have to draw complete machine diagrams there to understand this. That's why it is easily we can analyze in case of synchronous. Let's see for UPF load, case 1. Case 1, UPF load or purely resistive load it is. Purely resistive load. Now let us consider this is our alternator. Example, I am taking salient pole. Rotor field winding excited with DC voltage to create the required flux and rotating at synchronous speed. So based on direction of current in the field winding, poles will form based on flux direction upward. So here we get north pole, here we get south pole. So this is the field current direction. Flux will be in upward direction. So here south and north, and externally north to south flux will pass like this. And in the stator we have a 3-phase winding like this, a 3-phase winding. And let us consider the load connected to the alternator is purely resistive load. So it is supplying a 3-phase load here. Resistive load is connected. Okay, like this. Now a current will flow here, 3-phase currents. 3-phase current, armature current will flow. As it is 3-phase current, an RMF will develop in that rotating magnetic field. That is nothing but armature flux only. Armature flux is rotating at synchronous speed. Now here main flux it is. This is the main field axis. This is main flux axis. And this is also rotating at synchronous speed in same direction with the help of turbine. Okay. Now when there is UPF load, the armature current flows and armature flux develop, and how that armature flux will affect the main flux. So that is reaction between the two and how it is taking place and what effect will be there under this load. So for that we take reference main flux first. let us consider this is our main flux, reference I am taking. Now according to Faraday's law, due to this flux, whenever we rotate, first EMF induced in the winding, that EMF lags flux by always 90 degrees according to Faraday's law. The EMF induced lags flux by 90 degrees. Okay, let this is EMF, lagging flux by 90 degrees. Always, everywhere, flux, EMF always lags flux by 90 according to Faraday's law, rate of change of flux d phi by dt. Lagging is towards clockwise. Now this is EMF. Now load is connected, IA is passing. Actually we have to take terminal voltage, but right now we are not able to consider terminal voltage directly because load angle unknown for us. Let us neglect that. So directly with respect to internal power factor I am considering, that is load is UPF. So current IA will be in phase with the voltage. This is the current IA. Whenever armature current is passing, a flux will develop, armature flux. That armature flux also in phase with the current. Flux developed is always in phase with current. Now observe what is the effect of this armature flux on the main flux. How these two fields are present? Perpendicular to each other. These two fields are perpendicular. So the armature flux we call cross flux now. The armature flux we treat cross flux. And that effect of armature flux on main flux we call cross magnetizing effect. Cross magnetizing. If main flux is moving in this direction, these are the main flux lines, main flux it is, but armature flux lines is moving perpendicular to this, like this. This is armature flux lines. Now what is the effect of armature flux line with respect to main flux line? Perpendicular, that is cross effect we call, or cross magnetizing effect. So this effect we called cross magnetizing effect. This is called as cross magnetizing effect. Okay. Now what is the problem of cross magnetizing? Because of this cross effect, the main flux little distorted. The flux little bit distort. So whenever flux distorted, the EMF signal also little bit distorted. Slight variations will be there, harmonics will come into picture. But anyhow, this is not causing much problem to the alternators. Little bit cross effect will be there. But in order to reduce that cross effect, we need to create a strong main flux. The main flux should be very strong, so that much distortion will not take place. So we can avoid like that. Okay. Now whatever this excitation we given, DC supply we given to the field winding, this is called right now normal excitation. So we treat it as normal excitation. For example, let us consider the field current right now is 5 amperes. This is called normal excitation. Normal excitation. The amount of field current applied or excitation applied to the alternator under resistive load condition. We call normal excitation it is. Just reference we take it, so that what will happen in the next inductive load, capacitive load, we will observe it. Okay. This is normal excitation right now. Clear? Now same as it is, we will draw the phasor diagram for remaining cases, but every time I don't draw this diagram again. This is same, only load will change, resistor, inductor, capacitor, or RL load or RC load, like that. Okay. Now let's see case 2. If load on alternator is purely inductive load I take, 0 power factor lagging load. See what happened. Case 2. ZPF lagging or purely inductive load it is. See what happened. Again the same procedure. First main flux we have to take, because that is the responsible quantity for everything in the alternator. Without that, nothing, no voltage, no currents, nothing, no reaction. Okay. Now considering main flux. This is main flux. Now EMF lags flux by 90 degrees. This is EMF lags flux by 90 degrees. Now what is the load we connected? 0 power factor. Cos phi equal to 0 means angle is how much? 90 degrees. Current lags, purely inductive load, no? So current lags the voltage or EMF of alternator by 90 degrees. This is IA. Now armature flux will develop due to armature current. that armature flux will be exactly in phase with current. This is phi A. Okay. Now observe what is the effect of this armature flux on main flux. Main flux is moving in this direction, but armature flux is coming exactly opposite to that. They are both opposition, phase opposition, 180 degrees out of phase. Okay. So due to this, what is the resultant effect? If main flux is moving in this direction, this is main flux lines, but armature flux is moving exactly opposite to that. This is armature flux. Now the effect of armature flux on main flux is demagnetizing effect. So resultant flux, what happens? Simply decrease. That effect we call demagnetize. Flux in the machine decreasing, nothing but demagnetize. Flux increases means magnetizing effect. So right now we have here completely demagnetizing effect. Demagnetizing effect it is. Now what is the problem of demagnetize? Tell me. Because of this demagnetizing, the overall flux in the machine decreases, or flux in alternator decrease. Whenever flux decrease, what is the problem of generator? EMF decrease, and problem in motor is torque in motors will decrease. So some parameter definitely will be affected due to this reaction. Particularly if you talk about alternator, as some of the flux is reduced, the EMF of alternator slightly drops. So this drop we consider as drop due to armature reaction. So we represent this drop due to armature reaction in the form of reactance. That is armature reactance drop we call, IA XA drop. Armature reaction drop we call. Some voltage will be dropped. So that is not very much, approximately 2%, 3% of voltage, or in alternator generally it is more when compared to DC machines. DC machine very small drop will be there, very small drop because there is no reactance drop. Indirectly we take directly drop due to armature reaction with respect to flux. Separately with voltage we don't consider. In case of DC, drop due to reaction is some flux will reduce, some 1%, 2%, 3% flux will drop. That is we consider. Okay. But here in alternators we will represent the drop due to armature reaction in the form of reactance drop. Armature reactance drop. Okay. IAXA drop. Now finally, if you want to compensate this problem, what we need to do? So previously I said it is normal excited. Normal excitation under UPF load. Now what happened under inductive load? Demagnetizing, flux in the alternator decreases. Whenever flux decreases, voltage decreases. Proper voltages will not maintain at the loads. Suppose load required to be maintained proper voltage, same voltage. Now what we have to do? We have to generate same voltage. For that, whatever the flux is there previously before reaction, same amount of flux should be there. For that, what we need to do? Simply increase little bit this main flux. So during reaction, flux reducing, no problem, because some people will get a doubt. If you increase the main flux, they may saturate. Yes, if there is no armature flux, if you increase only main flux continuously, poles will saturate, no problem, no doubt. But during reaction, we are increasing, no? During the reaction, what is the overall flux in the alternator? Decreasing. So no saturation here. Then what you can do is increase little bit excitation at that time. That is called over excitation. So whatever is there previously, 5 amps here. Now 5 amps is normal excitation. Now little bit excitation we have to increase. Let some 8 ampere field current or 9 amps field current. So let us increase the field current. Increase the field current. This is we call over excitation. This is we call over excitation. So when alternator is over excited? Under lagging power factor or inductive load condition, we need to over excite little bit increase the excitation, so that whatever drop is taking place, that will be compensated. Same voltages will go to the load now also. Okay. So alternators under inductive load always over excited to maintain constant terminal voltages. Clear? This is case 2. Now let's see case 3, purely capacitive load, what happened. Case 3. case 3, purely capacitive load. ZPF lagging, zero power factor, leading it is capacitive, no? ZPF lead nothing but purely capacitive load. Purely capacitive load. Now again same procedure, consider the main flux reference. This is main flux. EMF lags flux by 90 degrees. Now as load is capacitive, purely capacitive, current leads the voltage by 90 degrees here. So armature current leads the voltage by 90 degrees. This is armature current, leads voltage by 90. If it is the armature current, armature flux will be in phase with this. This is armature flux. Now observe what is the effect of this armature flux on main flux. Check it is. What is the effect of this armature flux on main flux? Both are in phase or not? Yes. What happens to overall flux now? Increases. If the two fields are in opposite direction, then resultant flux will decrease. But right now both are in same direction. That's why if this is the main flux, see, this is main flux in this direction, and armature flux also coming in the same direction. Armature flux is also coming in the same direction. Now what is resultant flux here? Increased. This effect we call magnetizing effect. This effect is magnetizing. Now what is the magnetizing effect problem? Is it advantage or disadvantage? This is also disadvantage, because when there is magnetizing effect, overall flux increases. As overall flux under the poles increase, what is the EMF induced in alternator now? Will be beyond the limit. It may cause sometime insulation problem also, because sometime high voltage may induce, with that insulations also may damage, or if same voltage appears to load may damage. That's why we should control that voltage to again normal or nominal values. Same voltages should be there. So what we do here, in order to maintain same voltage, flux should not increase. Same flux should be there. For that we have to do now, reduce the magnitude of this flux. Reduce the flux now. How to reduce the flux? To reduce the flux, let us reduce the field current of alternator. Previous UPF condition, normal excitation 5 amps we given, and previously in inductive load case we given 9 amps of field current, example over excitation we call. Now what we have to do? Consider this is reference, normal excitation it is. Now whenever there is a capacitive load, we have to reduce the field current, that is called under excitation. That is called under excitation. So this is case 3. Okay. This is under excitation. Now example, you take the field current is IF equal to previous normal excitation 5 amps we taken. Now let us take some 3 amps. Little bit field current reduced. So this is called under excitation. So whenever alternators supplying capacitive loads, we should under excite. So important questions: when alternators under excited, when alternators over excited. So these are all repeated questions. Okay. So that's why we have to reduce the field current, that is we call under excitation condition. UPF case, normal excitation, inductive load, purely inductive load, over excitation, purely capacitive load, under excitation. Okay. Now let's see what happened in the next two cases. So these two cases important. So one is lagging power factor, other is leading power factor. Okay. Let's see now case 4. Case 4. See case 4. So case 4 is the practical case, which is lagging power factor case. So mostly in this case only the alternators will operate now, because practically loads are lagging. That's why let's see this lagging power factor. RL load. RL load it is. Now example, you can take 0.8 lagging, 0 power factor, maximum is unity power factor, and in between we have lagging some 0.1, 0.2, anything. So example, you take for example cos phi equal to 0.8 lag. Now let's see what happened, what is the reaction under this condition. Okay, same procedure, consider main flux it is, and EMF lags flux by 90 degrees, same it is, no change. So these two phases will never change. Now as it is lagging load, 0.8 lagging, what is the angle, power factor angle? 36.86. So current lags the voltage by some angle phi. Let it is IA and this is phi. And for example here 36.86 it is. If this is the armature current, what is the armature flux in phase with this? This is armature flux. Now check what happened. What is the effect of armature flux on main flux here? What is the effect? What is the effect of armature flux on main flux? This is not 90 degrees or this is not 180 degrees. So in between it is there. Okay. So we will resolve this armature flux into two components. So one is along this axis and other is along this axis. Okay. So this is we call phi A-D. This is we treat as phi A-C. What is C is cross magnetizing because 90 degrees it is with respect to main flux, and this is called demagnetizing component because it is opposite to this main flux, no, 180 degrees out of phase. So under this load we have two effects here. One is cross magnetizing and another one is demagnetizing. Two effects are there, cross magnetizing effect and demagnetizing effect. Now sometimes you may also get the questions, which effect is greater in magnitude, cross effect or demagnetizing effect? At which power factor both cross magnetizing and demagnetizing effects are equal in magnitudes? At 45 degrees. Suppose if the current lags voltage by 45 degrees, then this magnitude and this magnitude will get same. Magnitude of cross magnetizing component and demagnetizing component will get same magnitude when it is cos 45 degrees. What is cos 45? 0.707 lagging, 1 by root 2. Okay. Right now we have two effects here. Therefore the effect of armature reaction under this condition is we have cross magnetizing effect, cross magnetizing and demagnetizing effect. Both are there in this. Cross magnetizing and demagnetizing effect, both are there. It is not complete cross, it is not complete demagnetized, both the effects are included. Now tell me what excitation we should give to the alternator. Normal excitation for purely resistive load. Now RL load is there, L added here, inductive load, so that's why extra we got demagnetizing effect. So as there is demagnetizing effect, what should be the excitation of alternator? Tell me, we should increase or we should decrease? Whenever there is demagnetize, some flux will reduce, but not like previous so much reduction, little bit flux reduces. So when there is demagnetization, if you see the word demagnetize, flux in alternator reduces. So whenever flux reduce, EMF of alternator reduces or terminal voltages will reduces, some voltage will drop. Now load voltage gets fluctuate with this if it is single alternator supplying. Then what we have to do? To maintain the same constant voltage to the load, little bit flux should increase. How to increase? Now increase the main flux. How to increase main flux? By increasing field current. Little bit increase. Purely resistive load 5 amps we given, example, normal excitation. Now little bit over excitation required. Over excitation. Example, let the field current is now 7 amperes. Little bit increases, 5 becomes 7 amps. Little over excitation we need to apply. So this is the procedure we need to apply whenever it is applying a lagging power factor load, some 0.8, 0.9, anything. Okay. So if one important thing, this is unity power factor, this is 0.8 lagging, next 0.6 lagging means IA will come here, next 0.4 lagging, next 0.2 lagging, next 0. 0 means current exactly here, 0 power factor. So whenever power factor is decreasing, what is increasing? Observe this. Whenever power factor decreases here, the armature current shifting towards 180 degrees with respect to main flux. Means whenever IA moves in this direction, cross magnetizing component will decrease, demagnetizing component will increase. Whenever IA moving towards this 180 degrees, that is which is 180 degrees with main flux, whenever IA moving down, the demagnetizing effect increases, cross magnetizing effect decreases. You can consider by drawing different IS here. Okay. So whenever power factor decrease from UPF, demagnetizing effect increase. So as demagnetizing effect increasing, we also should increase the excitation slowly, 5, 5.5, 6, 6.5 like that. Okay. So excitation increases. Now what happened here? Is it good or bad? That is, increasing excitation of alternator is advantage or disadvantage? That is an advantage for us. We have to increase. Over-excited alternators always stable. Remember this point. Over-excited alternator is more stable than under-excited. So alternator operating at 0.8 lagging, alternator operating at 0.8 leading. At which condition alternator is highly stable? 0.8 lagging alternator is highly stable. But if you take 0.8 leading means under excitation we should apply. Next case it is. Whenever we under excite, stability of alternator reduce. So it will come in the stability topic. Just remember this point. Whenever excitation increase, whenever excitation of alternator increase, the stability of alternator increase. Okay, clear everyone this? Any doubt here? Any doubt? So like this we need to increase the excitation whenever power factor is decreasing. Okay, next. This is case 4, lagging power factor. Let's see case 5, leading power factor. Case 5. Leading power factor. Leading power factor means RC load it is. RC load. So let us taking example 0.8 lead. 0.8 leading I am taking. Now again same procedure. First take main flux reference. This is main flux. Then EMF lags flux by 90 degrees. This is common 90 degrees. Now where is the armature current? So 0.8 lag leading I taken. So 36.86 current leads. So current leads the voltage by some angle here. This is IA and this is the angle power factor angle it is. Okay. Next, when there is a armature current, armature flux will develop which is in phase with this current. This is armature flux. Now this armature flux is not 90 degrees with this or not in phase with this, in between is there. So this armature flux we resolve into two components again. One is along this component, one is along cross magnetizing phi AC it is, and other is along phi AM in phase with this, because in phase no magnetizing component it is. Now some part is cross magnetizing, some part is magnetizing. So two effects are there in this. Two effects. Therefore the effect of armature reaction is both cross magnetizing and magnetizing effect. Magnetizing effect. Okay. So as there is magnetizing effect is there extra. Due to that magnetizing, overall flux of the alternator increase. Magnetizing is there. So as flux increases, what happens to EMF of alternator increase? Then what happens to terminal voltage? Also increase. Then load may damage or insulation of alternator itself may damage. So we have to control that voltage. How to control is maintaining constant voltage. How to maintain constant? Now reduce the flux. How to reduce flux? Under excitation. Now let us reduce the field current of alternator. This is called under excitation. Little bit under excited. Case 1 is UPF load. What is the field current there? 5 amperes. Now let us reduce little bit, some 4 amperes. Field current applied. So it is under excitation we call. So when alternators are under excited, whenever it is applying leading power factor load, we under excite alternators. When alternators over excited, whenever it is applying lagging load, it is over excited. So to avoid all these confusions, simply remember 3 points. When there is resistive load, normal excitation. When there is only inductive load, over excitation. Or what is the effect of armature reaction? Resistive load, cross magnetizing. When there is inductive load, demagnetizing. When there is capacitive load, magnetizing effect. When there is RL load, RL, R means cross magnetizing, L means demagnetizing, both are there. When there is RC load, cross magnetizing and magnetizing. So when there is magnetizing, we have to reduce excitation, under excitation. When there is inductive load, demagnetizing effect is there. Demagnetizing means flux decreases. So we have to increase the flux. For that, over excitation we should apply. So resistive load, normal excitation, inductive load, over excitation, capacitive load, under excitation. So if you remember these points enough, you can understand anything. So this topic related with further whatever the topics we have, like voltage regulation topic or alternator characteristics, and one more is parallel operation mainly. Complete parallel operation, we have to answer the question by using this armature reaction topic only. So when it is over excited, when it is under excited, when it is demagnetizes, when it is magnetizes, all this. Okay. And if you know well about alternator armature reaction, sometimes they will ask, take care of this, a synchronous motor operating at 0.8 leading power factor. A synchronous motor operating at 0.8 leading power factor. What is armature reaction in that? Demagnetizing, what reaction takes place? 0.8 leading means RC load. R means cross magnetizing effect. C means for alternator magnetizing effect. But for motor you have to say opposite. For motor you have to say opposite. Okay. For 0.8 leading, what is the reaction for alternator? Tell me. Cross magnetizing and demagnetizing for alternator. No. For 0.8 leading in alternators, cross magnetizing effect and magnetizing effect. Leading, no. This one. Cross magnetizing and magnetizing. For alternator it is. So cross magnetize, magnetize. They are asking for motor. So right cross will come as it is. But here magnetizing will become demagnetizing in case of motor. Magnetizing in alternator, demagnetizing in motor. So this magnetizing, demagnetizing are exact opposite for alternators and motors. So first, whenever they ask alternator, directly you can say this, or whenever they ask for motor, first 1 or 2 seconds you try to remember for alternator first, and then say opposite to it. Cross magnetizing as it is you say, and remaining magnetizing effect will become demagnetizing effect, and demagnetizing effect will become magnetizing effect for motors. Opposite it is. So my suggestion is learn for alternator enough, and don't learn simultaneously for motor, because everything will be opposite there, we confuse. That's why learn only for alternator. Whenever they ask for motor, just to say opposite to this. That's it. Okay, synchronous motor. Same as it is, we have to draw the phasor diagram. But what is the difference is, in alternator current IA will be outside, current will come to the load outside. But in synchronous motor, same current IA will go inside. Current will become opposite just. Okay, so to avoid all this problem, remember for alternator perfectly and answer for motor opposite to it. Okay, so this is a small topic, a small information which will be so much useful to you further to learn any further topics and to understand easily further any topics in synchronous machines. Okay, so this is our topic today, armature reaction of alternators.
ESC, PSUs and other state service exams, mainly in the English, Hindi and Telugu languages. Hope you'll all going to make ACE online platform as a part of your success story. ACE Online. Learn anywhere, anytime. Wherever may be your present journey, but if you decided for your goal. Whatever may be your present position, but if you opted to reach higher altitudes in the life. However may be your present duties, but if you choose to find the joy of working. Whatever may be your present circumstances, but if you determined for your success. Yes, you rightly heard it. ACE online platform raises you much more than what you can think. This platform provides pre-recorded and online lectures which you can access around the clock. You can prepare for the various competitive exams like a GATE, ESC, PSUs and other state service exams, mainly in the English, Hindi and Telugu languages. Hope you'll all going to make ACE online platform as a part of your success story. ACE Online. Learn anywhere, anytime. Wherever may be your present journey, but if you decided for your goal. Whatever may be your present position, but if you opted to reach higher altitudes in the life. However may be your present duties, but if you choose to find the joy of working. Whatever may be your present circumstances, but if you determined for your success. Yes, you rightly heard it. ACE online platform raises you much more than what you can think. This platform provides pre-recorded and online lectures which you can access around the clock. You can prepare for the various competitive exams like a GATE,